Black-Scholes used a no arbitrage condition and a delta hedging argument to develop an option pricing PDE given the option payoff at maturity. For simple options like the European vanilla type options, the Black-Scholes PDE yields a closed form solution. However, for more complicated type options, Black-Scholes can be easily solved numerically using finite difference and Monte Carlo methods. Let us consider for a moment a European call option. Black-Scholes made the simple observation that the value of the call option and the price of the stock is positively correlated. They exploited this fact by creating a portfolio where they go long in the call option and short a quantity delta of the stock. And they recognize that if they carefully chose delta in a particular way, they can perfectly eliminate risk. And for a completely riskless change in the portfolio over a particular period of time, this would be equivalent to investing a similar amount at the risk-free rate. This idea, along with the stock price evolution in the form of a geometric Brownian motion model with constant drift and volatility, and the use of Ito's lemma yielded the Black-Scholes PDE. The Black-Scholes PDE is linear and homogeneous. This means that to value a portfolio of derivatives, we would just have to sum the value of each derivative in that portfolio. The PDE is of backward type, which means a final condition must be specified in the form of the payoff at maturity. The Black-Scholes PDE has two parameters, the risk-free rate and the volatility. The risk-free rate is easy to specify, and it has been shown that the option value is not very sensitive to the risk-free rate anyhow. The volatility, on the other hand, is very hard to measure, and as such, the Black-Scholes PDE can be seen as an illustration of the relationship between the option value and the volatility of the underlying. It may be surprising that the drift rate of the stock price does not show up in the Black-Scholes PDE. But this can be explained by considering that the option value can be perfectly hedged by investing in the underlying. And we should not expect to be rewarded for taking unnecessary risks. The Black-Scholes PDE has four terms: the time decay term, the convexity term, the drift term, and the discounting term. The time decay term tells how the option value changes with time as the stock price is held fixed. The convexity term tells how much on average we should expect from a hedged position as the stock price moves. The drift term allows for growth in the stock price at the risk-free rate. And the discounting term takes into consideration that the payoff is given at maturity, but the option is being valued today. I believe that the Black-Scholes model is a very good model because it is mathematically tractable and remarkably robust, which this means we can relax quite a few of its assumptions, and the Black-Scholes PDE still makes sense. For example, if we hedge discretely, the Black-Scholes model is right on average. We win sometimes, we lose sometimes due to discretization, but the Black-Scholes model still makes sense on average. To incorporate transaction costs, we just adjust the convexity term. To incorporate penalties associated with short selling, we adjust the risk-free rate. For time-dependent volatility, we substitute the root mean square average of the volatility over the remaining life of the option. For stochastic volatility, which is independent of and uncorrelated with the stock price, we just substitute the average of the volatility over the entire life of the option, conditional on its current value. For arbitrage opportunities which arise due to differences in the actual volatility and the implied volatility, then we use the Black-Scholes equation to determine the profit that we expect and use the delta formula to hedge.